Hello, this is Ms. Martinez, and in this video you are going to be learning about the basic differentiation rules. This is the video you have been waiting for. You're going to be able to find the derivative of a function using the constant rule, using the power rule, using the constant multiple rule, sum and difference rules, and find derivatives of the sine and cosine functions. So here it is. These are I don't want to call them shortcuts, because what it really was is people looking and proving rigorously that there exist patterns that allow us to do this work mentally. So let's get started. Oh, sorry. Yes, we're also going to find rate of change. Okay, so introduction. You all, up until now, have used the limit definition, which is the limit of the slope of the line there, the rate there, at a particular point. And what we're going to do is we're going to use these rules to be able to find it without using that definition. So here it is. Here is your first rule worth $1 million. Okay, the derivative of a constant function is 0 every single time. And if you think about it graphically, that makes sense because a constant function is just a horizontal line, and the slope of a horizontal line is 0. So I'm going to give you a moment to answer all of these. Please write the derivative of each of these constant functions. Pause the video and do so. All right, for the first, y prime would be 0 because the derivative of a constant is 0. Similarly, s prime of t would be 0 because the derivative of 45 is 0. F prime of x would be 0 because the derivative of 0, which is constant, is 0. And lastly, if k was a constant, well, pi is a constant. It's a value, it's a number, and so the y prime here would be 0. It's amazing. And you could prove this using the definition, the limit definition. And that has been done. It has been rigorously proven, and therefore we are able to use this pattern kind of rule. Similarly, the derivative of x is 1. Think about the line y equals x. The line y equals x is a line with the slope of 1. So the derivative of that single variable, f of x, f prime would just be 1. S prime of t would be 1, and if you were working with x of t equaling t, that would also be 1. Those are all the same function, it's just written differently. They're all graphed the exact same way, just denoted with different variables. So that was our second rule. Now, I want you all to take a moment here, and what we are seeing are the functions. These 4 functions are being all raised to a different power. These are called power functions because all it is x raised to a power, your variable raised to a power. So use your limit definition. I want you to do that and try to find the derivative of each of these functions. And look for a pattern. And then use your results to write your best guess on how or what the derivative of f of x equaling x to the n, what would that be? So try and do that without looking ahead. Just take out a piece of scratch paper real quick and try and work those. Pause the video and we'll check them in just a moment. Alrighty. Well, the first one, f prime, would be, well, it's what we just saw. Of a single variable is 1. And you just proved it. Okay. Now, what about of this quadratic here? It would be, if you did it correctly, 2x. For c, f prime would be 3x squared. And for f of x equaling x to the 4th power, that would be 4x cubed. Okay, so what is happening here each time? When you had a power of 1, the answer was just 1. When you had a power of 2, it was 2x, and now the power is just 1. When it was 3, when it was raised to the 3rd power, it is then 3x, and it's only being raised to the 2nd power. And lastly, when you had f of x equaling x to the 4th power, the derivative was 4x to the 3rd power. Ladies and gentlemen, here's what happens. You take the power, let's say that the power is n. N becomes a constant that you multiply the function by. And the power that you were working with, n, is decreased by 1. So you essentially bring down the power and write it as a coefficient and decrease your power by 1. And that works for any power that you're working with. Let's try some together. We already know the answer to this, to the first and second. To the first, you bring down the power 2, and you decrease the power by 1. 2 minus 1 is 1. It's the almighty 1. You don't have to write the 1 there, but you know he's there. All right, so f prime, you would bring down the 4 and decrease the power, so that would be 4x cubed. Now this isn't written as a power, problem C, but you could write it as a power. It's to the 1/2 power. So f prime would be 1/2 x, because you take and you multiply it by the power. The power, the original power, I guess, becomes your coefficient. And then you decrease the power by 1. So 1/2 minus 1 is negative 1/2. Problem D you could rewrite as x to the negative 1 power. So negative 1 becomes your coefficient, and you would decrease your power by 1, which would make it a negative 2. But you can write that in the denominator, and that would be correct, because using your negative power rule, if it was x to the negative 2, you would move that down, as you see in D. All right, so E. You can pause and try and do these last couple if you'd like. The power, you could rewrite this as x to the negative 2, which means negative 2 is going to be your coefficient, and you would be decreasing by 1. So negative 2 minus 1 is negative 3. That is why we have x to the 3 in our denominator. And this last one, you could rewrite this as x to the negative 2/3 power. So negative 2/3 is going to be your leading coefficient. And if you take away 1 from that, that's like taking away 3/3. That's going to be negative 5/3. And you could write all of that in the bottom. You could write that in the bottom with the 3, so that it would be negative 2 over 3 times x to the 5/3. But I don't believe I did here. So let's look at our next rule. All right, here, what do? When you have the derivative of a term like such, where you have a number times a power function, all you end up doing is multiplying that number, we'll call it a, times the derivative of your power function. Let me show you in some examples. Here we have 3x x squared. So what we do is we take the derivative of our power function and multiply it by that constant. So you would be bringing down the 2, so it would be 3 times 2, which is 6. And you decreased your power by 1. So it is x to the power of 1, which we don't write because that's non-essential. All right, now b. You're going to take the derivative of your power function. So that would be taking down the 3, multiplying the 3 in front as a coefficient, but it already has a coefficient. So you would take the product, which is negative 15, and decrease your power by 1. That would be t squared. For problem C, I would rewrite it so that it is in an exponent form. And now you're going to multiply. You're going to multiply a times your power. So 6 times 1/2. It gives you 3, and then decrease your power by 1. That's going to be a negative 1/2. You could write it like this, removing the negative power by putting it in the denominator, and the half power is the square root. So that's just another way of writing that. Here, this one would be 3x to the negative 2. So we multiply our coefficient times our power. That would be negative 6, and decrease the power by 1. That would be x to the negative 3, which you can put in the denominator. If you want to pause the video and try these last couple on your own, feel free. They are kind of like cool, challenging, fun problems. All right, I would rewrite it for x to the 1/2 power, which means we're going to have the negative 2x, and oh man, I typed that wrong. Okay, what would that be? You would be taking away 1 from 1/2, so that would be negative 3/2 in the denominator. My bad. Too many problems. I made a mistake. All right, you'll have to forgive me. Let's look at the last one here. I would rewrite it. It would really be negative x times x to the negative, because it's in the bottom. It's 4/3 because you're taking and raising x to the 4th power, but then also taking the 3rd root. Okay, so now you're going to multiply those. Negative 8 times negative 4/3, that is negative 32/3. And you're going to take away 1, so that's like taking away 3/3. 4 minus 3, that's going to be your negative 7/3, which you can put in the bottom so that you're not working with negative powers. I just had a really corny joke because we don't work with negative powers. We are positive people. We don't want to use our powers for bad. We want to use them for good. Get it? Positive, good powers. Okay, sorry. I just couldn't help myself. I had to share that joke. Let's move on before I say any more bad jokes. All right. If you're working with a sum or difference of functions and you're trying to find the derivative of them, just take the derivative of each and add them if you were working with addition, or take the derivative of each and subtract them if you were working with subtraction. Let me show you what that looks like. Here, we have a whole string of terms. We're going to use all of our rules like kind of at one time here. And we'll just take the derivative of each term. So with this first one, you would bring down the 3. You'd be using your power rule. So bring down the 3 and decrease the power by 1. That's 3x squared. For the second one, you're using your power rule again. It would be negative 10x, and now our power is 1, and we don't write it. For the next one, the power is 1, so 2 times 1, that gives you 2, and you decrease the power. It was 1, now it is 0. X to the 0 power is 1. So that's why it's just 2. and the derivative of a constant is 0, I don't really need to write anything there because plus 0 doesn't mean anything. That would be the derivative for the first one. Why don't you guys try the next few? All right. You'd be bringing down the power for x to the 5th. So that would be 2/5 times 5. That gives you just 2x to the 4th. The next term, pretty straightforward. Alrighty, now let's look at b. To find the derivative here, you'll take 5 times 2/5, which is 2, and decrease the power by 1, that's 4. The second term, the derivative is 4x cubed. The third term, the derivative would be 6x, and the derivative of a constant is 0, so we can leave that off. Now, in part C, I would rewrite this function so that you are looking, or you're seeing more clearly, the exponent that correlates with the roots that are being taken. Now you can go ahead and write that out, and it would be 1/3 x, and then taking away 3/3 would be a negative 2/3, and that would be 5/2 x, and taking away 1 from 1/2 is negative 1/2. All right, this one, a lot is happening here. You would multiply 5 times 3/2, which is 15/2, and taking away 1, which is 2/2, would give you 1/2. The next term, negative 6 times 5/3, that's actually going to be 10. And taking away 3/3 would be 2/3. And the last one would be 4x, and it would be to the negative 2 power. That's why the 4 becomes negative, because originally your x was to the negative 1 power. Now, we can go through, no, never mind. All right, now, a little bit more sum and difference rule problems. For the first one here, you would have, for the first term, it would be 6x. For the second term, you would multiply negative 4 times 2. Oh, you know what? That should be a positive because it's times a negative 2. So that should be 6x plus 8 over, and then x to the 3rd because we increase that power. Or you could think of it as decreasing negatively. All right, and then the last one, we're looking at, you would have 2 to the 1/2 power, so that would be 1/2 of 2 is 1, and then taking away from 1/2 would be a negative 1/2, and that is why the root is moved to the denominator. In problem F, okay, it is all over x, and so the first step when you have something like this, you would want to go ahead and divide every term by that value. So that would simplify to the following, and then you can take the derivative of each term, which would look like this. And if it asked you to put it back into that same form, you would go ahead and begin by writing that last term, making the negative power positive, and dividing every single term by, and multiplying it by x squared. This is going to allow us to then write it all over x squared, so that your final answer looks something like what the original problem was. Alrighty, this last rule is the derivative for the sine and cosine functions. The derivative of the sine function is cosine, and the derivative of cosine is the opposite of sine. And I just want to show you here a little visual demonstration so you can see how these are connected. The first graph is the sine function, and right at this point the derivative would be 1. And if you take a look at your cosine function at 0, it is 1. Up here at pi over 2, the derivative would be 0, and taking a look at your cosine function at pi over 2, you do see that the graph is 0. At pi, it would be -1. And at 3 pi, and if you look at your graph at pi, it is at the value of -1. And at 3 pi over 2, the derivative would be 0, and that point is on your cosine function. At 2 pi, the derivative would be 1, and you will look at your cosine function and you'll see that at 2 pi, the graph is at the value 1. And we could do similarly looking at the cosine function, and whatever the derivative is, it would be the opposite of your sine graph. So that's just kind of a visual to help you understand that a little bit more. Thanks.